Hello friends, today we're going to be talking about topic 2.8, part 1, inverse functions. Okay, so the idea of an inverse function is that it undoes, I like to think of it, right, a function as an input-output. So in an inverse function, we're just switching the output and the input, right? The output becomes the input becomes the output, and not the foot that's outside, the output. And what we do is, if we have an equation, then we can actually just solve for the input variable, right? So every inverse relationship can be found by switching, switching each x, and that's supposed to say y there, every x and y values, okay? It's important that we understand the concept, right? Because it might seem intuitive, but we get a whole bunch of different types of problems, and we need to be able to think through why we're doing what we're doing. So here's a very, very simple example, right? Input, output, find the inverse relation of the given table. Well, all we're doing is switching the input and the output. So we have -1, 1, 2, 3, 0, 4, and 2, 6. Now, notice that two inputs, we have the input 2 here twice, but we have different outputs. So that means this is not a function, because remember, a function has to pass what's called the vertical line test, that for every input, there is one and only one output, right? There can be multiple outputs for different inputs, or the same output for a bunch of different inputs. But every single input has to have only one output. And the second thing fails that. Okay, so the original table is a function. I should be writing. The original table is a function because each x value has only one y value. Okay. However, the inverse is not a function because the x value, 2, has two different outputs. Has two different y values. Okay. And then graphically, when we're taking the inverse of a function, what we're actually doing is we're reflecting over the line y equals x. So we're like reflecting over this line. Okay, it's like we're reflecting over this line. Every x and y value we can switch, right? So for example, this point right here is 4, 3. So there's going to be 3, 4, right? That's the inverse of that value. Then we have 2, 1, so 1, 2. Also, when it crosses this line, y equals x, the inverse will also cross that line, right? Because the output and the input are the same. That's what that means. And so here I have -1 and 2, so I'm going to do 2 and -1. And then I have -2, -1. So I'm going to -1 and -2. Okay, and so this is what this inverse looks like. And you can see it's a mirrored image over the line y equals x. Okay, and you can create a table for that if you need to keep track of the numbers, right? So the graphs of inverses are reflections over the line y equals x. Okay, now when we actually have equations, what we can do is switch the xy variables and solve. Okay, so for example, find the inverse for f of x equals 3x minus 7. So what I do is I'm going to rewrite this as x equals 3y minus 7. Okay, now I'm just solving for y. Okay, and the way that we write the inverse is like this. It looks like f to the -1 of x. All right, and it's tempting to think of that as like, think of it as an exponent, right? As if this is like, oh, this is 1 over f of x, right? No, that is not what that means. This is function notation, and so the function notation of f to the -1 means the inverse function of x, right? or inverse f of x, we can call it. All right, so again, when you've got an equation where you know what the input-output machine is, you can just switch y in for the x's, put in x for the f of x or for the y, and then again you're just solving. Sometimes it might get messy, especially if you've got like a fractional polynomial, something like that. But that's the process, right? And then the final version, you rewrite it as f to the negative 1 of x equals, and then like for this example we had written, it would be that. All right, but let's do a couple of examples down here. Okay. So I'm going to switch. I'm going to put in y for the x's. And now I have to solve for y. Okay, so there's some steps there. It's just algebra of solving for y. And then I replace that with inverse f of x equals negative 3x plus 2 over x minus 1. And let's try it again with this one. Okay, so just some steps from algebra. Once you do the substitution of x and y, just solving for y. Same thing as last time. Okay. So to find an inverse, we switch the x and the y values. Right. And so graphically, again, this means that the inverse will be a reflection over the line y equals x. And if a graph is not made up of simply of line segments, what you can do is take particular points, right? Find particular points, and then flip them, right? Or switch them. So you sketch the y equals x line on the graph, sketch that line like I did before, and then mark any points that are already on the line. Because remember, any points where it crosses that y equals x line, they're going to stay there. And then you add some additional points on the original graph, and then find their inverse points. All right. And you can find the inverse points by switching x and y values, or by drawing a line perpendicular to y equals x, and then find the points that's an equal distance to that line on the other side. Let me explain first. Okay, so here's a graph. So I'm going to sketch the line y equals x. Okay, now I've got a couple of points that cross that line. I also have a few points that are kind of at grid points that I can see where they are. And so what I know that I can just switch. You know, I have 2, 0, so I'm going to go to 0, 2, like that. Right, this point and this point, those that are on the graph or at the intersections I can leave. And then I also have 0, 4, so I'm going to go to 4, 0. Okay, so what this is going to look like now is like this. Okay, so it's the original is a parabola, and what I've done now is I've created a sideways parabola. What we mean by the thing setting a perpendicular line and then going an equal distance, if you were to take a line perpendicular line from this point to this point, right? So that perpendicular line would look like this. All right, this kind of orangey line, pretty close, right? This orange line is perpendicular to the y equals x line, and then I take this point is one diagonal away, so I put the inverse of this point is going to be one diagonal away, but over on this side, right? So equal distance to the y equals x line, but on the other side of that line. So same thing over here too. If we take a look at this other point that we had labeled, I'm going to do this. Oops. Okay. So here, from the y equals x line, I've got 1, 2 diagonals this way. So the inverse point is going to be, or sorry, the original is this way over here, right? 1, 2 diagonals. So the inverse is 1, 2 diagonals in the opposite direction. So that's what we mean by that. I don't find that one particularly helpful, that method, but maybe you will, and maybe it'll work in particular situations. Let's try B. Okay. So again, I'm going to draw the diagonal line, y equals x. Okay, now I'm going to mark the points where it's already crossing, because those points are still going to be there. Okay, and now I have, make these points a little bit bigger, easier to see. Now I'm going to take some significant points and find the inverses of them. So this one here is 1, 0. So now I'm going to go to 0, 1. Write these points like that. Other points up there. I have the point here, negative 2, 0. So I'm going to go to negative 2, or 0, negative 2, which is over here. Okay, I also have this point. What is this? Negative 1, 2. So I'm going to go to 2, negative 1, and that'll give me that point. Okay, what's this going to look like? Right? Well, it's coming in like this, curving around, and then like that. Okay. Notice again, like if you folded this over the y equals x line, then the black line and the blue line would match up. Right? They'd be on top of each other. Shows that kind of symmetry. Okay. So if you plug a number into a function, it will generally output a new or different number. For example, if we plug x equals 2 into the function f of x of 3x minus 1, we get 5. Okay, now if you plug that answer into the inverse function, the answer should be 2. Right? So that when you take the output and put that into the inverse, then that gives you the input that created that output in the first place, in the original function. Right? Right? Inverse functions, they undo a function. It's just switching the input and the output. And so if you plug x, any number x, into a function, and then plug the output into the inverse, you should end up with x again. Okay, and so that's one way of checking functions. Right. So we can write it this way. To show that two functions are inverses, you have to show that inverse of f of x. And so here we're looking at composite notation. Right? We already saw this in the last section, and so we're using that now as we discuss inverse functions. And you have to show that f of the inverse function are both equal to x. Okay. So here's an example. It says let f of x and g of x be the functions below. They're given here. And now determine if they are inverses of each other. Okay, so f of g of x. So I'm going to take 2, and then instead of x, I'm going to plug in the function g of x, and then continuing f of x minus 3. So now I'm just going to simplify and see what I get. And it works. Let's try it the other way now. Good. So f of g of x equals x, and g of f of x also equals x. So that means that they are inverses of each other. Okay, sometimes we have to use a restricted domain to ensure that two functions are inverses. So for example here, show that h of x and k of x below are inverses where x is greater than or equal to 10. Okay, and you can see that for k of x, right, we can't put any values in there that are 10 or less, or that are less than 10. And so that's where the restricted domain is coming from. But in order to show that they're inverses, I have to plug one into the other. Now, when I've got this, in this step right here, I have to specify that x is greater than or equal to 10 because of where that came from. Right? In the original function, that's there, and so x has to be greater than or equal to 10. But it's not explicit in the way that I've written it here, so I make it explicit here. Now we do k of h of x also. Okay, and here I get, the square root of x squared, absolute value of x. But since x is greater than or equal to 10, I know that the absolute value of something greater than or equal to 10 is just going to be the value of what it is originally. Okay. So now example 8. Again, n and p of x show that they're inverses as long as x is not 0 and x is not 4. So for n of p of x, this is going to look like 6 over, instead of x I write 6 over x plus 4 minus 4. Okay, now again, x cannot be x cannot be 0 in this function because p of x has x in the bottom of a fraction. And so now when I simplify, I get 6 over x over 6 plus 4 minus 4. That just cancels out. And I end up with now this is just equal to x. Right. But again, with the restriction that x is not equal to 4. And then for p of n of x, so I had 6 over x minus 4. And so here, x cannot equal 4, right? Because I've got x in the denominator of the denominator. This simplifies, right? So 6 over x minus 4. I always like to think of dividing as multiplying by the reciprocal. So this is actually 6 times x minus 4 over 6 plus 4. The 6's cancel out, of course. And now I end up with x minus 4 plus 4, which is equal to x. So they are inverses of each other, given those domain restrictions. Thanks for watching. Don't forget to like and subscribe.